Previously, we've talked about the concepts of microstates and macrostates, and we've started to develop a picture of the microscopic picture of these thermodynamic quantities. So we're moving into what we call statistical mechanics, thinking about how the statistical properties of the individual molecules in a gas are leading to these thermodynamic quantities like temperature and energy, and then now we're getting into entropy. So we want to go a little bit further in this lecture to think about what is the microscopic interpretation of entropy. And we'll use those concepts of microstates and macrostates to do that. Okay, so that's basically the whole goal of this lecture, is to think about what is entropy and how do I relate it to what the gas molecules are doing. You've probably heard in your life entropy. If you ask somebody on the street what is entropy, some of them might say, oh, it's disorder. But then I want you to go a little bit beyond that. So my goal here is to get beyond the idea of what is of entropy being disorder, and just if I ask you, well, what does it mean to be disordered? That's the idea. So what's the formula for entropy, and how is it related to disorder, and can we go a bit beyond what it means to be disordered in terms of equations and physics? In the pictures here, these are pictures of Ludwig Boltzmann. So he's one of the pioneers of statistical mechanics. The left one is a younger version of him. The right one is his tombstone, which is in Vienna, and you all should visit it. And if you notice on his tombstone, one of my favorite physics stories is that he has an equation on his tombstone, and the equation on his tombstone is obviously what everyone considered to be his most famous or most important contribution, is exactly the concept of this lecture. So this equation that we'll be talking about today is on Boltzmann's tombstone as one of the most important contributions to science. Okay, so let's go back to thinking about an ideal gas as a bunch of molecules moving around. Previously, we talked about a microstate and a macrostate as being, the macrostate was like how many atoms are on the left side, and the microstate was the particular atoms which were on the left side. But if we want to do thermodynamics, we need to kind of redefine this notion. So now let's think about, I want to think about a macrostate a little differently. Macrostate for this gas is going to be the thermodynamic state, which is the state that we've been talking about in the first few weeks of this course. Thermodynamic state is specified by state variables like the pressure, the volume, the temperature, the entropy, the internal energy, all of these things. So it has all of these properties. It has a pressure, a volume, a temperature, entropy, internal energy. So that's the state, that's the macro state of the system. What's the microstate? The microstate is what the individual atoms are doing. So that's the detailed position and momenta distribution of the gas molecules. So I got to know exactly how are the atoms arranged in the box and what's their momentum distribution look like. So how fast are they moving? That tells me how fast they're moving, tells me about their kinetic energy, which tells me about the temperature and the internal energy. Okay, so first thing I want to do is let's think about these positions. So I want to know how many ways can I arrange n gas molecules in this box. So we're going to say there's n gas molecules. And I'm going to divide the big box into a bunch of small divisions, okay? So I'm just dividing it into a grid here. And I'm going to say there's B of those boxes. So I'm dividing my volume into a number B boxes. Okay. The question is, how many ways can I put the n atoms into these B boxes? Okay, and now you're wondering how big are these boxes? So actually the size doesn't matter. The size of the boxes is irrelevant as long as they need to be big enough so I can fit more than one atom in each box. So don't make the box the size of an atom is the upshot, but as long as you have some division, some number of boxes, or some B number of boxes, which I'm calling B, the actual number is not going to matter. Okay, so suppose you had one atom. How many possibilities for places could I put that atom? There would be B possibilities to put it, to place it, right? So I'm taking my atom, my first atom, and I want to know, I can put it in any of those boxes, so there's B ways to do that. What if I had two atoms? Well, I have B possibilities for the first one, and I have B possibilities for the second one. Because I could fit more than one atom in each box. So the total number of possibilities is the product of those two, B times B, which is B squared. And hopefully you can see how this goes. Now, what if I have n atoms? There's going to be B to the n possible arrangements. By the way, when we were thinking about whether the atoms were on the left side or the right side, B was 2. I had divided the box into 2 pieces, and the number of possible arrangements was 2 to the n. We did it for 4 atoms, and we got 16 possible arrangements. That's 2 to the 4 is 16, right? So this is just doing that same thing again, except I'm having more divisions, not 2, not dividing left and right, but dividing into a bunch of pieces. And this is the total number of ways that I can arrange the atoms. And let me write this now. B is going to be the volume, it's going to be the volume total volume divided by the volume of a box to the power n. Because the total volume, V, maybe I can write it up here, is B times the volume of a box. So the total number of ways that I can arrange the atoms goes like V to the n. That's really the key point. So it's proportional to the volume to the nth power, where n is the number of atoms. Okay, so we've started trying to think about the number of ways that I can arrange gas molecules into a box with volume V. So this volume is, V is the total volume. And the way I kind of got to it was I said, let's divide it into a bunch of small pieces which have the volume V box. And then we tried to count up all the ways that I could arrange the molecules. If there's n atoms or molecules, then the number of ways that I could arrange them in those small boxes was what I call omega, the multiplicity. The number of ways to arrange it is the total volume divided by the volume of the box to the power n, depending on how many atoms you have. So now let's consider the free expansion.
Let's do our favorite experiment, which is you have the gas confined into one side of the container, and then at some time you remove the partition and you allow the gas to expand. What happens to the multiplicity? What happens to the number of ways that you can arrange the gas molecules in here? Well, hopefully it makes sense it's going to go up because it has you have more places for the gas molecules to be after you allow it to expand. So omega final, that's after the expansion, is V divided by V box to the n. And omega initial is V initial, V box to the power n. And if you take the ratio of those, omega final over omega initial, you get Vf over Vi to the power n. Okay. And happily, that V, the volume of the box, cancels out. As long as I deal with this ratio here, I don't need to worry about what the exact size of the box is, which is good because I just made it up, right? So it's good that it canceled out of everything physical. Now we're trying to make a connection to entropy. So let's think, how does entropy figure in here? We have a formula for the entropy change in the ideal gas. And let me write it out for you. Oh, there it is. And in a free expansion, this will be 0 because the temperature doesn't change in the free expansion. So I've got delta S is number of moles times R natural log Vf over Vi. And I've got that same ratio, the Vf over Vi, here and here. So I can make a connection now between entropy and multiplicity, or number of microstates. The problem is I've got a natural log here. So in order to make the two formulas look the same, let me take the natural log of this one up here. So let's go up here. Let's take natural log of omega f over omega I is the natural log of Vf over Vi to the power n. And then let's use the rule for logs. I can take the n outside. Natural log Vf over Vi. So I can take this here and substitute it in here. So we're going to combine those two formulas. And what do I get? Delta S is equal to number of moles, Nm, R, and now instead of natural log Vf over Vi, I'm going to write 1 over n times the natural log of omega f over omega I. Okay? And this prefactor can be simplified because remember that n is the number of moles times Avogadro's number. And so I get here R over Na natural log of omega f over omega I. And R over Na is Boltzmann's constant. So this thing here is Boltzmann's constant. So I get the important formula, delta S, change in entropy of the gas is Boltzmann's constant Kb times the natural log of omega f over omega I. So what does this mean? It means that if the entropy went up, it means that the number of microstates, or the multiplicity, has gone up, right? So let's make this a little bit more precise on the next slide. So we've made a connection here between S, which is a macroscopic state variable, and the multiplicity, the number of microstates, small omega. We can go a little bit further. Delta S is S final minus S initial. And I can separate out the log Kb natural log of omega f minus Kb natural log of omega I. And now you stare at this, it's not too hard to identify. This can be S final and this can be S initial. So we're able to identify S, entropy, is KB, natural log of omega. This is Boltzmann's famous formula, which is on his tombstone. It tells you what entropy is. What is entropy? It has to do with the number of ways to arrange something, leaving the overall appearance unchanged. And that's where the disorder part comes in. So when the gas is constrained to be just on this one side, the number of ways that I can arrange the gas molecules on that one side is small. So it has a low multiplicity. If I allow the gas to expand, then there's more places for the gas to be, and so the number of microstates has gone up and the entropy has gone up. Okay? So something which is ordered is something, a macrostate, which can only be achieved a few ways. Something which is disordered is a macrostate which can be achieved many ways. So when you say entropy is going up, you're saying that the number of ways that things can be arranged is increasing. Let me try to give an analogy of this. So the analogy I like is, imagine you're standing at the corner of your bedroom with a bunch of socks and you throw all the socks into your bedroom. Most likely, the socks are going to land all over the place in the room and it's going to be messy, right? So it's a disordered room. It's because there's a lot of ways that it could be messy. There's tons of places that the sock could be in the room. What is very unlikely is for you to throw the socks and they all land perfectly in your drawer, folded. That's something you've never seen. That's an irreversible process. And the reason you've never seen that is because there's very few ways that the socks can be ordered in the drawer. Right? There's very few ways that you can order them perfectly in the drawer. There's many ways you could order them like anywhere in the room. So when you throw the socks up, because it's much more likely for them to be spread out everywhere in the room, that's a state with a high multiplicity, and it's a state with a high entropy. So that's the connection between order and disorder. So hopefully you know what it means for something to be ordered or disordered now. Something which is disordered has a large multiplicity. There's a large number of microstates which lead to the same macrostate.